In the previous subsection, we established the formal framework of time-dependent perturbation theory. We wrote the exact wave function as a superposition of the unperturbed stationary states with time-dependent coefficients a sub n of t. In this way, the effect of the time-dependent perturbation was transferred into the time evolution of those amplitudes. This led to a coupled system of differential equations for the coefficients a sub n of t. However, that coupled system is generally too complicated to solve exactly. So in this subsection, we introduce the perturbative solution method for the amplitudes themselves. The key idea is to expand each coefficient in powers of the perturbation parameter. We then substitute this expansion into the coupled amplitude equations and collect terms order by order in lambda. This gives us a hierarchy of equations. The zeroth order equation, which describes the unperturbed system, the first order equation, which gives the leading correction to the amplitudes, and the second order equation, which gives the next correction, and so on. So the goal of this subsection is to show how the state amplitudes are determined systematically, one order at a time. This development is very important because these amplitude corrections will soon lead us directly to the transition amplitudes and transition probabilities. So in short, the previous subsection established the mathematical framework, and this subsection begins the actual perturbative solution of the amplitude equations. Now let's look at the zeroth order equation. In the absence of perturbation, lambda equals 0, then apparently these terms are gone. So we find that the time derivative of the zeroth order amplitude is 0. This means that every zeroth order amplitude is constant in time. This result is exactly what we should expect physically. In the absence of the time-dependent perturbation, the amplitudes of the unperturbed stationary states should remain constant. Only the phase evolution is already included in the exponential phase factors, as shown. So the zeroth order solution corresponds to the unperturbed system. No transitions occur among the unperturbed states, and the probability associated with each unperturbed eigenstate remains constant. In other words, in the absence of time-dependent perturbation, the occupation amplitudes in the unperturbed basis are constant. However, we noticed that a strictly time-independent probability density requires that the system is either in a single unperturbed stationary state or in a special superposition of stationary states. In general, constant coefficients or occupation amplitudes alone do not guarantee a stationary probability density for every superposition. This is the essential content of the zeroth order result. So from here onward, the zeroth order amplitudes serve as the known inputs to the first order equations. Next, we examine the first order correction terms. After substituting the perturbation expansion of the amplitudes into the coupled amplitude equation and collecting all terms proportional to lambda, we obtain this equation, which can be further expressed in a more compact form as shown, where we have dropped the time dependence of the expansion coefficients, since we have just shown that the zeroth order amplitudes are constants. This is the fundamental equation for first-order time-dependent perturbation theory. We will interpret it physically on the next slide. Let's interpret the fundamental equation that we just obtained. In first-order time-dependent perturbation theory, the time rate of change of the first-order correction to the probability amplitude of the nth unperturbed state is given by this equation. It suggests that state m is connected via a perturbing Hamiltonian to all unperturbed eigenstates. The change in the probability amplitude of state M is driven by contributions from the unperturbed amplitudes A sub n naught of all states n, with each contribution determined by the perturbation matrix element H sub m prime of t and modulated by the oscillatory phase factor e to the I omega sub mn t. So as time evolves, the state n can be viewed as feeding amplitude into or removing amplitude from state M due to a time-dependent perturbation. Therefore, the time-dependent perturbation redistributes the probability amplitudes of all states. In a word, the time dependence of the coefficient A sub m of t means that the probabilities of finding the system in different unperturbed eigenstates change with time. Please also note that the summation over n runs over all unperturbed states, including n equals m. So one of the terms in the sum is given by this expression. Therefore, the nth state can contribute to the time variation of its own first-order correction through the diagonal matrix element of the perturbation, which is H sub m prime of t. So this equation tells us how a weak time-dependent perturbation begins to transfer amplitude among the unperturbed eigenstates. This is already a very useful result because in many practical problems, the initial condition is especially simple. For example, if at time equals 0, the system starts entirely in one unperturbed state, say state I, then we have A sub n naught equals delta sub ni. In this case, the sum collapses and the first order equation becomes much simpler, as shown here. This is the standard starting point for transition amplitude calculations. Now we collect the results obtained so far and write the wave function to first order. We still have the equation for a general solution of the time-dependent Schrödinger equation as shown. But now, to first order in the perturbation, the amplitude of each unperturbed eigenstate is given by this equation. So the first order approximate wave function becomes the equation as shown. This is the first order perturbed solution. Now let's interpret it physically. The coefficient A sub n naught represents the stationary amplitudes the system would have in the absence of the perturbation. The correction terms A sub n1 of t describe how the weak time-dependent perturbation begins to redistribute amplitude among the unperturbed eigenstates. So the perturbed wave function is obtained by taking the known unperturbed basis states and modifying their coefficients in time according to first-order perturbation theory. This is why time-dependent perturbation theory is so powerful. Once the unperturbed eigenstates are known, the effect of a weak time-varying perturbation is encoded entirely in the time evolution of the coefficients.